Welcome back, scholars. Today we will continue looking at how to solve trigonometric equations with a focus on quadratic type examples. Let's get started. In this first example, we're asked to solve an equation where the left-hand side is a 3-term expression. Notice that the left-hand side takes the form ax squared minus bx minus c, which is a typical quadratic trinomial form. Recall that we can factor this left-hand expression using a variety of techniques. We'll end up with the pair 2 times sine squared of x plus 1 and sine of x plus 1. Since the right-hand side is equal to 0, we'll set each factor equal to 0 and solve, just like we would solve a quadratic or other factored form polynomial. On the left, I'll subtract 1 from both sides and then divide both sides by 2. I've got sine of x equals negative 1/2. That will be the angles 7 pi over 6 and 11 pi over 6. On the right, I'll add 1 to both sides of the equation, generating sine of x equals 1. That will be the angle pi over 2. Now, these are our algebraic solutions because they were generated using algebra techniques. It is also possible to solve this equation by graphing. In this case, we would graph the left and right-hand sides of the equation separately. Note that since the right-hand side is equal to 0, that will just be the x-axis. In other words, the solutions can be visualized on the graph as the points where the left-hand expression and the x-axis intercept. In other words, the x-intercepts. We can see all 3 of our algebraic solutions when graphing a single cycle from 0 to 2 pi. In our next example, you can see that we have 2 different trig functions present on the left-hand expression. We'll need to use our trig identities to make a substitution here so that our left-hand expression is written in terms of only one trig function. Using our Pythagorean identity, I'll substitute sine squared of x as 1 minus cosine squared of x. I'll combine like terms and multiply the entire equation by -1 to eliminate the negative leading coefficient. This reverses the sign of every term. Next, I'll use that same trinomial pattern to write the left-hand side in factored form. That will be 2 times cosine of x minus 1 times cosine of x minus 1. We'll set each factor equal to 0 and solve. On the left, that will be cosine of x equals 1/2, which will be the angles pi over 3 and 5 pi over 3. On the right, that will be cosine of x equals 1, which will be 0 radians. We can visualize these solutions a couple of different ways. First, on the unit circle, we can see the solutions pi over 3 and 5 pi over 3 in quadrants 1 and 4. We can also graph the left-hand side of the equation and find all the values where the function is equal to 0. These are visualized as points of intersection at the x-axis. Let's look at another example. This time, we have cosine of x plus 1 equals sine of x. We have 2 things to manage here. First, there are 2 different trig functions in the equation. Second, we'll need to collect terms containing variables on one side of the equation to solve algebraically. We'll start by squaring both sides of the equation. This generates a sine squared x on the right, which can be replaced with a 1 minus cosine squared x using the Pythagorean identity. We'll collect all of our terms on the left-hand side, setting our equation equal to 0. Then we'll factor out the greatest common factor from both terms. That will be 2 times cosine of x. Last, we set each factor equal to 0 and solve. On the left, we need the angles where cosine is equal to 0. That will be pi over 2 and 3 pi over 2. On the right, we need the angle where cosine of x equals -1. That will be pi. Now, before we move on, we need to pause for a second here and contemplate these solutions. In order to generate these solutions algebraically, we substituted one function for another in squared functions. If we were to visualize these transformations, we would find that the graph changed subtly, and potentially enough to introduce extraneous solutions. So we will need to verify each solution. We do this by replacing each solution angle into the original equation. We find that pi over 2 is a solution, pi is a solution, but 3 pi over 2 is not a solution to the original equation. We can visualize the solutions graphically by plotting the left-hand and right-hand sides of the equation separately and looking for the points of intersection. Using our graph, we can visually confirm the solutions pi over 2 and pi, and we conclude that 3 pi over 2 is not a solution. Let's look at just one more. We have cosecant and cotangent of x equals 1. Once again, we'll need to write this equation in terms of a single trig function. I know that cosecant and cotangent can be written in fraction form using the reciprocal identity and the quotient identity respectively. From here, I have common denominators, so I'll just add the numerators. I'll square both sides of the equation and make a substitution for sine squared of x using the Pythagorean identity. Next, I'll collect all variable terms on the left side of the equation and write the left side in factored form. After setting each factor equal to 0, I find that x equals pi over 2 and 3 pi over 2. Since we made a substitution that changed our function type, let's verify each solution. I'll substitute each of my answers into the original equation to check. It looks like pi over 2 is a solution, but 3 pi over 2 is not a solution. Once again, to graphically check these solutions, we would simply plot the left and right-hand sides separately and look for points of intersection. We see the solution pi over 2 is the only solution over the interval 0 to 2 pi. All right, that wraps up our second look at solving trig functions. We'll see you next time.